Alrighty. So here's the lesson outline. So as kind of discussed in the first video, we're going to talk about the writing process, specifically introduce a software development process to you. Then we're going to get into language syntax and semantics from a general standpoint, and then finally conclude with the classic first program in C++. So the writing process. This is quoting from Bjarne Stroustrup's Principles of Programming. Programming is fundamentally simple. Just tell the machine what to do. Well, thinking about this, we have all been given descriptions of tasks to complete. For instance, when I first arrived in Champaign last fall, I was unaware of how to get to Siebel from where I'm currently living. So I, opened up the maps, typed in my home address, put in the endpoint, got into my car and followed the directions from here to campus, and then went undergone COVID testing, took 12 hours to get the result in, and then did the same thing over tomorrow and walked into my office for the first time. I haven't been back since. So the question becomes then, okay, if we've all kind of, gone through this process of, following or completing different tasks by some sort of, process, whether linear or otherwise, what makes programming so difficult? Well, computers must have everything described in detail. They have no common sense to compensate for incomplete instructions. So thinking back to my example of getting from home to campus, there's a lot of things that I kind of subconsciously went through to make that happen. For instance, I had to get up from my chair. I had to walk down the hallway, outside the back door, open the garage, open the car door, back out of the driveway, get onto the street, follow the rules of the road, and eventually arrive at campus, then figure out the whole parking scenario upon my arrival. If I'm a computer, I don't know what a hallway is. I don't know how to stand up. I have no conception of a car, of walking, of driving, of turning the ignition over to start it, of backing up. What's a street? What are the rules of the roadway? You don't know, or the computer doesn't know. You do, of course. And what makes programming so difficult is you have to account for like every step in that whole process, as minuscule and as obvious as, a particular item may be. So one must precisely and unambiguously describe what to do to the computer using a language with a specific grammar. It can't be like English where that's kind of loose and there's, you can get away without being as specific and direct. And then what you also need, in addition to this very specific and refined grammar, is a well-defined vocabulary for the actions that we would like to perform. This is quoting more or less from Stroustrup's text that was referenced on this slide. Programming languages are going to be used towards this end. So here's kind of the level that you have to think about it from. When writing code, we're going to provide the computer with a sequence of instructions that are going to be executed to perform a computation or solve a particular problem. Think in terms of this. You need a detailed recipe for a cook to follow during the preparation of, say, some dish. I don't know, I'm feeling chicken piccata, so we'll throw that in there. In order to actually execute that dish in the kitchen, if you have all of the ingredients, weights, temperatures, etc., you can go through the motion and hopefully get pretty close to the dish you were expecting. I always seem to be a little off, but more or less there. With a computer, you need to be just as specific, and if not more. There's no conception of cook me some chicken piccata or something as broad as that. You need the actual sequence of steps at a very refined level in order to implement an algorithm or application to perform that computation or solve that particular problem. What it really comes down to, and I'm quoting the first or second chapter of Stroustrup's Principles of principles and practice using C++. This is what I used when I taught at Texas A&M. I've probably read the book, I don't know, at least 5 times cover to cover. So I'm quite familiar with it, and I like how he puts, some things, specifically this. Programming is understanding. When you program a task, you understand it. If you don't understand it, there's no way that you're going to be able to program a task to solve some sort of problem. You really need to understand it inside and out. So a significant amount of time in this course will be attempting to understand the tasks that you are trying to automate or the problem that you would like to solve. This includes MPs. So with that in mind, let's take a slide aside and go, well, what do we actually want from our programs? Well, perhaps most obvious is correctness and reliability. We want, given some set of input, a correct output that is reliably computed. The second thing that we're interested in is a well-designed application, in the sense that we want it to do something productive, something that helps us. If we simply, have a correct and reliable program that outputs something that's, of no interest to us, I mean, what's the point of that program? There isn't one. So we do want a well-designed program. And finally, for this course, this will be perhaps, I guess, one of the more kind of pressing subjects that will really encourage us to write programs that are maintainable. If you think about it, perhaps not on the small sorts of projects you'll be doing in this class, but once you get out there and, eventually graduate and have a job, you're going to want to write maintainable code. That is code that someone else could sit down in front of and be able to make sense of it and be able to improve it. Because any program that is, worthwhile, we're expecting it to stick around for a while. So when we're interested in creating these maintainable programs, we're going to want to essentially implement the requirements as simply as possible. We're going to want to write self-documenting code, so using good variable names, good structure. And in addition to that, we're going to want to provide ample comments to clarify regions that are not intuitive to the reader. And this isn't only to help those who come after us and who perhaps could be tasked with improving or modifying, correcting, etc., our program or code base that we wrote. It will also help, a future us if we need to go back and revisit some code. I remember during my PhD, I wrote I guess we can call it an application, and then I put it on the shelf. I hadn't visited it for about a year, and then I came back to it. Couldn't make sense of, how I implemented this thing. So I ended up spending, I don't know, 2 to 4 weeks rewriting the whole application. And it was the biggest, waste of my time ever. But at the end, I think it takes like one scenario like that where you go, okay, I really need to make this maintainable, because since that event, I mean, my whole processes have really changed, because I just want to avoid that in the future. I don't want to have to worry about that. So how do we go from kind of some problem to a solution? What are some ways to think about that? What are some approaches that seemingly work? Well, most software development processes, and if you've, had an internship or you've taken a software engineering class, you'll know there's a ton of different processes out there. But most of them have these 4 phases. There typically is some sort of analysis component. It could be named something different. Then there's a design phase, an implementation phase where you're, actually coding, maybe writing tests and debugging. And then in many, you have a repeat or some sort of cycle where you go back through these processes, and the duration of the time spent in each process, the stakeholders who are involved, etc. It all varies depending on the process that you're employing. But for this class, we're going to keep it relatively simple and just cycle through these 3 stages. So what do I mean by analysis? This is all before we sit down in front of the keyboard. We're going to figure out, given maybe it's a machine problem. So given some sort of machine problem, What are the requirements that we're going to derive from that specification? What are the possible problems within that prompt that I need to solve? What is my current understanding of those problems? If I don't understand it, it might take a little bit of background research to say, go look up a concept, clarify what it means, for something to be of that nature, etc. There is frequently some background work that goes into this to, really solidify your understanding of the problem you're looking to solve. Then the next step is to figure out, okay, what is the process that I must go through to solve these problems? I would kind of think about, how would I solve this in a non-automated way by hand to start? Just, thinking about it. If there's mathematical, components, maybe working out the formulas. If it's, you know, some sort of, I don't know, maybe card game that you're looking to implement, or I don't know, chess, checkers, etc. Figure out how the game works, or, those components. What are the processes that you have to go through to win? What are the rules? What are the regulations, etc.? And then once you've kind of figured out the general case, are there any edge cases or fringe cases that need to be considered? Are there any constraints that you should acknowledge? Once you've gone through the analysis stage, the next step up is going to be design. This is where you're going to sit in front of a whiteboard, hopefully, or, pen and paper, and start to think about different structures or ways that you could actually design the underlying system to solve your problem. So you might consider, how does the program flow? I'm not a huge fan of flowcharts, especially with more complicated systems, but, just sketching out kind of the initial flow of how you expect data to move through your program can be beneficial, especially on the sorts of machine problems that you'll be solving within this course. Once you've kind of figured out how things should flow, the next step is to decompose that into individual parts that can make up the whole system. Obviously, we don't want some huge long bit of sequential code. We really want to compartmentalize this and break up and create essentially subsystems that can solve, various components of the problem, and then we can put that together in the end. The next step is to obviously start thinking about the interfaces to these different components and how they might communicate with one another and the relationships between them. That's definitely, going to take a little bit of time as well, but it's also, in my opinion, a lot of fun. This is, the more kind of creative side of the whole process. And it's, if you like sketching pen and paper, it can be a lot of fun. And then the last, thing you want to consider in your design is, are there any libraries out there that could help me solve this problem? Has anyone done anything similarly that I could look in terms of their actual, influence towards, my overall solution? Because you don't want to reinvent the wheel. It's just time not well spent. So the key takeaway in this phase is going to be to focus on problem solving. I would even stay away from, pseudocode and really begin diagramming, but pseudocode might be okay here, but definitely not explicit implementation and coding details that are at a low level or communicate something very specific. So the documentation of this process should definitely be language agnostic, and it should not be written in any sort of programming language. So the next step is going to be to actually implement your design. And implementation has 2 or 3 parts depending on how you want to look at it. The one that most students really enjoy and get excited about is writing the code. In fact, there's so much excitement that typically, you'll see people skipping the analysis and design stage and really trying to get into solving a problem in a new language without kind of going through the motions in their native tongue first. So again, I'd strongly, and this, it'll seem like it's going to take more time, but it's a good investment. It'll pay off. So after you go through the analysis and design phases, you'll begin writing code. Okay, that's only part of the implementation. The other part is going to be debugging the code that you've already written. And in addition to that, testing the code to ensure that it actually does what it is supposed to do. And for debugging and testing, we'll get into some informal and formal ways of doing this, I believe, in the second week of class. So that will be coming soon. You'll learn a lot about that. And we'll expect you to carry that through the entire semester. In fact, when it comes to, say, getting help in office hours, we're going to expect you to be able to say, I added this line of code and something break, or my expectations up to this point in my program are X, Y, and Z. And here's what I think is going wrong. What we're not going to necessarily entertain is, long sequential spaghetti code without, kind of a clue where the problem could be. So what we're going to see here is it's kind of going to be, you write a little code, you debug a bit, you test it, and then you move on and you keep, it's almost like a mini cycle within the implementation phase that you'll go through, just to ensure that we don't write the whole solution and then test at the end only to find out there's multiple things wrong, and then trying to determine, okay, well, is one issue dependent on another? And it becomes a lot of work. It's a lot of kind of cognitive load. So if you incorporate or disperse a little bit of testing in with the writing, huge benefit in my opinion. And then here's kind of where the whole process begins a cycle is, once we've gone through the analysis, design, and implementation phases, we're likely going to need to repeat these process. So a combination of thinking about the problem, so analysis, and experimentation, design, and implementation help us acquire the understanding required to implement a satisfactory solution. What that means is you probably won't get it right the first time. So you might be going through your implementation. Maybe you realize that there's a lot better way to structure your solution. Maybe there's a better approach. You'll frequently go back to the drawing board, revise your strategy, and then, implement those revisions and kind of continue on. So therefore, the development process is frequently going to iterate through these phases. So analysis, design, and implementation. And your actual solution is going to be built out over multiple iterations of this process. The last thing that I want to point out, and it's within the text I keep referencing, is that feedback is crucial. And there's half a page that kind of goes into why feedback is crucial. So Strostrup early in this section points out, learn from experience, and we modify our behavior based on what we learn to kind of move forward. And that's the learning process summed up. So what you could do is you could open up a editor, test out your ideas by programming them, compiling, and trying to determine, whether or not you're on the right track, or if, or even if that kind of idea is a feasible solution. Okay. That's not the best way. It's often easier to write down design ideas and walk through them, even if it's explaining them to an inanimate rubber duck. And this is called rubber duck debugging. Essentially, it's just speaking out loud, walking through the process. Because if you cannot explain your ideas aloud, how could you possibly implement them in a programming language? It would be very difficult, because obviously your understanding of the problem is not sufficient to begin coding. What I'd encourage you to do, where you're allowed to within the course, is to discuss design and programming techniques with friends and colleagues, again, to the extent that it is allowed. So you couldn't do this for a machine problem, although I believe the syllabi says you could, at a really high level, clarify different sorts of components of the prompt, but you obviously couldn't talk about the implementation. But a great area for this is going to be in the lab sections, where you'll be working collaboratively with your peers and, trying to come up with a solution to some sort of prompt. And I think there's a lot to be said about walking through this with others, hearing their perspectives as well as sharing yours. And in addition to that, having the opportunity to hopefully clear out any misconceptions about, say, a particular concept, technique, or otherwise with them, or even just, going back and forth kind of about different approaches to an implementation. You can learn a lot in the process. And again, it's highly encouraged to do this before reaching for the keyboard. But again, when and where appropriate. So with that, I'm going to go ahead and end this video, and then I'll move on to the language syntax and semantics section, and then we'll eventually move our way down to that classic first program, and then this lesson will conclude.